Hi, everyone. Welcome to this YouTube live event celebrating the Richard Nelson Thomas Award for graduate students in astrophysics at GILA. My name is Anne-Marie Madigan, and I am an assistant professor in the Astrophysical and Planetary Sciences department here at CU Boulder, and I'm also a GILA fellow. Over the next hour, we're going to hear from past and current recipients of the award, the chair of GILA, Professor Andreas Becker, and our guest speaker who's here today, Dr. Selma de Mink. Dr. de Mink is the scientific director at the Max Planck Institute for Astrophysics in Germany, and she'll be giving us a talk about her research and also the importance of graduate student mentoring. To those watching on YouTube live, you'll be able to ask Professor de Mink questions using the chat window, and I'll be able to pose them to her in the last about 10 minutes of the event. So for some brief history of the award, the Richard Nelson Thomas Award for Graduate Students in Astrophysics at GILA was established in 1996 by friends and family of Richard Nelson Thomas to provide an annual award to the year's most outstanding graduate students in astrophysics. And this is voted upon by the Astrophysical Fellows at GILA. It's hoped that this award will keep Dr. Thomas's legacy of scientific leadership current in the minds of young astronomers as they begin their careers in fields that he loved. This year's recipients are Lauren Matilsky from Professor Yuri Tumori's group and Heather Wernke from my own group at GILA. So now we're going to see a short video of the past recipients of the award, and then we will hear from Andreas Becker, chair of GILA and a professor in the physics department.
It was really meaningful to me to receive this award because I did a joint thesis where part of my thesis was studying relativistic jets that are emitted from active galaxies. And the other part of my thesis was in science communication. And I had received recognition for the work that I'd done in science communication before, but this was an award that was really specifically for the astrophysics research that I was doing and recognizing, how I was contributing to that field, and that meant a lot.
It's always nice to receive recognition, especially, as an early career graduate student.
I received the award just last year and certainly wasn't expecting it at all. So it was very exciting to learn that I had received it. And just the impact of that I'm so grateful and thankful. I've learned so much in my time here at CU, and to be given an award at the end of that time I'm just super grateful for that.
Well, it's really nice to, see my work recognized. I've worked in GILA for since 2015, so my whole PhD, which has been almost 6 years at this point. So it definitely feels nice, and it gives things a little more flexibility, like financially.
It was a nice bit of recognition that somebody other than, my PhD advisor cared what I was doing in that small office in the GILA Tower every day.
My current position, I work for the American Astronomical Society, and I'm the editor of a publication called WS Nova. So my work is communicating the research that's been produced recently across the field of astronomy. And so, the award just contributed to my feelings of confidence as an astronomer and put me in a position where I felt prepared to take on a role like this, where I'm really, taking in a lot of astrophysics research and digesting it for the broader community.
Right now I'm a staff scientist at the Los Alamos National Lab, working on computer simulations of hydrodynamics and radiation hydrodynamics. And that's what I was doing. I was doing similar work along those lines in graduate school. And so that's where I am now.
It's going to be really, really helpful for me as I move forward. I'm heading to the University of Mary in North Dakota, and I'm going to be a physics professor there. So it's going to help me a whole lot with the move and getting settled in, and really just being a professor there.
Yeah, I mean, it definitely motivated me. To be honest, I've struggled a bit with motivation during the pandemic just because things were, I don't know, like time was kind of a blur, and it was kind of hard to delineate like work life from home life because we're all working from home. Yeah, and the award definitely kind of hurt my spirits up. And it was like, okay, no, there's people who actually care about what I'm doing. So yeah, it was overall very nice.
The whole JILA experience really helped me understand what I wanted to do professionally and gave me opportunities to do it. So in research, I had opportunities to do research that, had an impact, within JILA and within the broader community. The award was a nice indicator that research mattered.
Well, I would say first off, feel good about the work that you're doing, because clearly somebody believes that it's worthwhile and that you're really contributing to the community. And in terms of advice for the future, I would say pursue whatever it is that you're passionate about and find your niche. There's a lot of ways to really work with specifically what it is that you consider to be your strengths. And this award kind of points out that you have strengths and you can go find them.
I suppose the advice I would give somebody is to just pursue what you're interested in, whatever that might be. It doesn't necessarily matter if other people think that's interesting. I think, if you're motivated to work on a problem, it's a lot easier to be productive. So just, pursue what you're interested in, even if it's not the most trendy thing.
So my advice would be just keep working hard. And whatever you're going through, you'll make it through. It is possible to make it to the end. Yeah, it's going to be great.
Having been on the other side of hiring processes now, the fact that an applicant can point to not just, I've done research and published papers, but that I've won awards for that research. It really speaks to the quality of the candidate. And so I think awards like this at JILA are very important at showing others, right? Showing people that they're going to be reviewing applications from students at JILA, that those students are valued and appreciated, and that those students have done something worthy of recognition, which I think made a difference in the trajectory of my career path. Going from a grad student at JILA through postdoc years, and finally in a faculty position of my own, and onward from there.
Okay, thank you for this very nice video. My name is Andreas Becker. I'm a professor at the Department of Physics, a JILA fellow, and I'm currently the chair of the JILA Institute. I would like to take also the opportunity to welcome you all to this very special event that we can have today. And I'm happy to see that the role of graduate students and the role that graduate students play in research is actually highlighted in today's event. Student mentoring is a central part of our mission at the Institute. Therefore, it's always great for me to see that each year with the Dick Thomas Award, we can give out such an award to one of our great astrophysics graduate students. I would like to take a moment with you to reflect on the JILA Institute and on the impact that Dick Thomas actually had on the development of JILA, so that it became one of an institute that is now known around the world. You might have heard from people working at JILA and from those who have visited GILA that they consider GILA as a special institute. And much of this, what makes GILA special, is something that we call a secret sauce, which has ingredients actually already from the very beginning. It was set by the founders of GILA, and Dick Thomas had a big impact on that from the very beginning. Now, I cannot highlight all the secret ingredients, but I would like to talk about two of these special ingredients. First of all, it's the GILA structure that has been given by the founders of GILA to the Institute. The Institute is run by the fellows. It is not run by the chair. The chair, like me, has actually no power. I'm a representative of the fellows to the higher administration. But all decisions that are made at GILA are made by all the fellows together. This is very different from many other institutes and departments that you see in the world. And it has a big impact. It means that as fellows, we are used to this, that we have to find a consensus on all the decisions that we are making. It means that we are listening a lot to each other, that we are listening to our arguments, to our different opinions. And it means also that everyone at each time is involved in the Institute and in the development in the Institute. All this creates a very collaborative atmosphere already, and it creates it contributes to the collaborative research atmosphere that we have at the Institute. Now, the second thing that I would like to highlight is something that Dick Thomas had a big impact on at the very beginning. He was one that brought up the idea that we should have a visiting fellow program. And that is something very special that we had over all the years and that we still have and that we all value very highly. So besides regular fellows like Anne-Marie and myself, who are working year-round at the Institute, we are having other researchers who are coming to the Institute, not just for a day or two to just give a talk, but who are coming for a certain time to stay at the Institute and work with us on a specific topic, being involved in a theoretical calculation or being involved in an experiment. Now, back in the last century, when GILA started, visiting fellows came for a whole year. They stayed a whole year at Boulder. They came with their family, with their kids. The kids went here to school, etc. Now, this is not what this is now anymore, due to financial constraints, but also to constraints that on many of us are that we cannot go for a whole year to a different institute. Now, visiting fellows are coming for 2, 3, 4 years. But the idea is still the same. They are coming, they are working with each other. It creates the exchange of ideas, and it contributes to the very open atmosphere that we have. And many of them are leaving GILA and becoming friends of GILA, actually. So it helps and supports GILA for a long time. So this visiting fellow program that was brought to us by the founders, and with Dick Thomas having a big impact on this, is actually one of the very important secret ingredients of GILA. Now, there is much more that makes GILA special, and I cannot talk about all of this, and Dick Thomas had a lot of impact on this. But I'm very happy that today we have this event and that we are highlighting the role of graduate students in this. And with this, let me turn it back to Anne-Marie, and I'm looking forward to the talk that we will hear soon.
Thank you, Andreas. Now, I'm delighted to introduce Dr. Selma de Mink, a scientific director and member at the Max Planck Institute for Astrophysics in Germany. Professor de Mink is most known for her work on the lives, deaths, and afterlives of massive stars, particularly those in binary systems. She's an expert on the evolution of such systems, some of which evolve into binary neutron stars and binary black holes. And these subsequent mergers can now be detected through gravitational waves. Professor de Mink studied physics and mathematics at Utrecht University, completing her PhD on stellar evolution at low metallicity. After holding several prestigious postdoctoral fellowships, including both a NASA Hubble and an Einstein Fellowship, I only know of one other person who's done this, she joined the faculty at Amsterdam University in 2014, before moving to Harvard University as professor in 2019. Since late 2020, she's now a scientific member and director at Max Planck Institute for Astrophysics. Now, I've known Professor de Mink, or Selma, since her days in the Netherlands as PhD students, and I've always found her to be a wonderful role model, particularly for women in astrophysical theory. In 2017, she set up a private Facebook group, so not everybody can join, but it's called the Old Girls Network in theoretical and computational astrophysics. This is a place we all share online resources, including jobs. We ask for advice and support when needed. And this is a place for junior members to find inspiring peers and role models. As Professor de Mink writes, while you may often find yourself to be a minority in your research group, at conferences, or in your department, you have in fact more amazing female colleagues than you may have realized. So with that, I'm going to turn it over to Professor de Mink, and I'm really looking forward to your talk.
Thank you so much for that, Anne-Marie. Let's see, is my screen sharing correctly? Yes, thanks. Yeah, thank you for the invitation to speak here. This is very special. I must say I have denied many opportunities to speak because I just moved and I felt that this is very hard to speak over Zoom. I love to be in front of an audience and actually see your faces. So but I'm glad I see two faces here on the Zoom video. But, so you asked me to say a few things about my research. I'll keep this part light. I think the real experts in the room may not learn very new things, but I hope they still find it inspiring to see this in connection with the work of Richard Thomas. Just briefly, where's my... Yeah, so I'm calling in from Max Planck. It's the end of the day here. So we're starting a new institute there. And my role today is not to advertise the institute, but this is the only small advertisement. If you're interested in these topics, we are, of course, very much welcoming your excellent graduate students, especially those that you award prizes to. But why we are here today is to celebrate the award of the Richard Nelson Thomas to two of your students. And I must say, I was not fully familiar with his work before, but I really enjoyed reading a little bit about him. There's a beautiful obituary about him that I recommend that this picture is from. Sorry for the dark picture. And so there's two things that are fascinating, I think, about his life and I find inspiring. And the first is his passion for understanding astrophysics, in particular, understanding how stars work, specifically the outer layers of stars. How do spectra form and the light that we see from these stars? And another topic that he's been interested in is stellar winds from these stars. And so I believe that not some of his opinions were a little controversial, but this passion is something I absolutely share. And so secondly, he was clearly a passionate supporter of graduate students, at least in the ways that he could in his time. And so in particular, he writes about young researchers in financial trouble that he personally helps out. So I don't know the full details of these stories, but this is very admirable. And so accepting to speak here today has a personal aspect. I think we went all through interesting and tense times during Corona. Around that time, I also moved institute a couple of times, and I think this has been very hard on my students and my group. And so I think it has been a time for me also to realize that I'm not always the advisor that I would really want to be. And I've been reflecting a lot on this. And so I took this as an opportunity to reflect on these topics. How can I or we be a better advisor? And this is also because of my new role. I won't only be responsible for my own students, but also for those in the whole department. So I partially took this on as a learning experiment. The first topic, I think I'm somewhat of an expert on. The second part, I'm absolutely not an expert. I'm here and happy to speak about it because I think it's an incredibly important topic. But I'm not here to tell you how to do this or what we should do, but to open the debate. So to start with this story about stars, I think the most fascinating thing I learned reading up on his history is that he did his PhD in Harvard. I spent 1.5 years there, and for me, this is a fascinating place, most of all because of Cecilia Payne, who was there, who's not only a hero for me, but also someone who really changed our view on the universe, or what the universe is mostly made of, at least the material that we can see from stars. So it was, I think many of you know her history possibly better than me, but for those who don't, she was a student in the UK, very interested in studying astronomy. And she took lectures from Eddington and Niels Bohr even. So she learned about astrophysics and about the atom at that time. But it was in a time where she could not get a PhD. Talking about graduate student support, she was not even considered to be able to be one. And so she took this knowledge, thinking about stars and how about atoms work. And she took this to Harvard because Harvard was allowing students to graduate. Well, actually not Harvard, but she could graduate at Radcliffe College. And so she made astonishing discoveries at that time that were controversial, and it was very hard for her to do a PhD. But understanding the spectra of stars is something that Richard Thomas continued on and that we shared. And so I want to tell you a few things about stars, starting a little bit from classic stories to what we are discussing today in terms of stars. And so I want to start with this picture. So the most important insight into stars comes from the most basic properties that you can even see with your naked eye in principle. Well, this is not something you would see by naked eye. This is an image of Hubble taken of a dense star cluster, Omega Cen. But even if you look up in the night sky, you can see that stars come in different brightness. Some are brighter and some are fainter. And you can, if you look very carefully, see that they have slightly different color. Some are a little bit redder than the others. So that's exaggerated in this image. And there's something special about this group of stars because they're all at the same distance. And that means that if they're brighter, they're truly brighter and not just closer by. And so this is a fantastic animation, and I think it's the most beautiful I've ever seen. And so I'll show you in a moment what would happen if you look at all these stars and you sort them by color and by brightness. And so that is an animation made by my colleagues, Jay Anderson and Roland van der Marel. I was a postdoc there as well. So it's, so I'm really hoping this comes through somewhat smoothly. I think we can share the link. So what's happening now is they literally took out little images of these stars and they're sorting it by color. I hope I can pause it for a moment. Yes. So it's sorted by color, and now we do the same, but now they're sorted by brightness. So many of you that took stellar classes know this diagram. This diagram is named after Hertzsprung and Russell. And not to distract too much, but Henry Russell was the person that tried to convince Cecilia Payne not to publish her big findings. And this diagram is named after her. But a lot of the work behind this diagram that looked much simpler at the time was done by the women that were at Harvard and that were colleagues of Cecilia. And so what you see here, this is, of course, a beautiful animation, but it was real data. And the stars are really at the location in this diagram where they should be. And so it's fascinating that you go from this chaos of colors and brightnesses into this structure. And so the laws of physics are behind this. So this was not understood at the time that Richard started the studies, but it has been. And the big advance came mostly, I think, around the 60s when our first computers were able to compute through the laws of physics. So conservation of mass, conservation of momentum, conservation of energy, nuclear reactions you need. So if you put these equations together in a one-dimensional system, that's okay in one dimension because stars are spherical, you can really compute and understand the structures in this diagram, as most of you know probably. And so this is fascinating. At that time, there was just a handful of stars in this diagram. And today we can make these beautiful images where we can even see the sequence of white dwarfs here on the left. I hope that still shows up in your videos. If you see the actual versions in the papers, you can see this. So this has been dramatic changes in our understanding how stars evolve. The original version of the diagram is old, but I would like to talk about a bit new work. Those stars you saw there are mainly low mass, typically a bit lower mass than the sun, because these clusters are so old. And so most stars that we have are actually less massive than the sun, red dwarfs. So this is from outread images that Paul Crowther put out. And what he wanted to show is that stars can get very heavy. I like them if they're about 10 times as heavy as the sun. And the record holder is now about 200 times as massive as the sun. So it's a pretty recent result. We didn't quite know what the most massive star would be. Most people would stop at 100 solar masses, 120. It's still a big mystery how they're formed, because it's so bright that the gas is pushed away harder than the gravity is trying to pull it towards each other, but still they exist. We're debating the masses. And I didn't say this, I gave this talk, the most luminous stars, and it's a reference to one of the first books that Cecilia Payne also wrote. So I want to talk about these very massive stars because they have very interesting lives. They can die, as you probably know, and end their lives as supernova, leaving behind neutron stars or black holes. And that's fascinating for the later part of this talk. This is something even more fascinating, I think. We tend to think if we see the stars in the night sky that they're individual dots, and that's not true. Most of them have a companion star. And for massive stars, this is so common that the majority of massive stars will have a moment in which they form a system like you see here. And so this is an artist impression, but the fact that we know this is based on spectroscopy measurements. And so these are two stars that are so close that the gravity of the star on the left is actually pulling more on this gas that is in between them, and it's sucking the material out of this first star. So this is something fascinating. We're making computer simulations of trying to understand and trying to get more data. And so this was known for a long time that such systems exist. It looks very exotic, right? It's exciting, but it's not exotic. So this is something that majority of massive stars go through. So we contributed to this insight, but you're definitely not the first. This goes back, if you want to the 1700s. Mitchell was already the first to understand that the location of stars in the sky were more often correlated than they should be, and that there should be a physical bond between them. Much later, we started to understand that they're so close that they can truly interact. That is relatively new insight. This is not all, I didn't want to talk about this, but by now, this was 2012, it's already old news for most people in our community. More recent insight is that about 20% of stars have even a third star that they interact with. So that makes our computer models much more complicated. Why would you care? I know there's many people interested in stars in your department, but when I was a fellow, and I also met you and Marie at that time, there seemed to be less interest in stars, and most departments were either doing exoplanets or thinking about galaxy formation. But even if you think about galaxies, this is very important, right? Stars, in particular massive stars, they formed through cosmic time, and their elements and explosions created all the enrichment of the gas that we're now made of. So they're really part of our own cosmic history. And so for this reason, we see massive stars really as engines that largely drive and set how galaxies change in shape and enrich themselves. And at the same time, if you look at galaxies or stars very far away, you look at mostly the light of the bright young stars, and it's usually the massive stars that's still alive. And so for a long time, we have been ignoring that these stars are in binary systems. For simplicity, assume them to be single. And so this is affecting many interesting questions of the role that massive stars play today. So there's a large body of papers pointing out where this matters and where this is not. It would be too much to discuss today. There's a second reason maybe to care, and that is other excitement. So I tried to explain to you that this is very common. This is not on the right. As I'm hoping people recognize what is on the right there. This is already 5 years ago. This goes fast. This is a signal that's extremely exciting. I know people that have even tattooed it on their arms because it was such a big discovery. It led to the Nobel Prize in Physics. And what you see here is strain. And strain is the amount by which something is squeezed or stretched. And this is the amount by which we all were squeezed and stretched in September 2015, because a gravitational wave passed through the Earth and it squeezed and stretched us all. And I bet you were not sensitive enough to detect such a small changes, but the LIGO detector, and here you see the data from Livingston, was sensitive enough to detect this. And so this has been world changing in our field, at least in our insight. These waves were predicted by Einstein, and it is the first direct detection of these waves. And so this is rare. What we think this is two black holes in a binary system going around each other with almost the speed of light, like 40% the speed of light, and in that moment merging into one single black hole, and with it shaking space-time so much that the energy output per second at that point was more than all stars that shine in the universe together, but emitted in gravitational waves, not in light, right? So that's rare. It's about 1 out of 1,000 stars or so or less do this. So the left is very common. One of the questions we're discussing is how do you form these pairs of black holes? And to show you why this is so exciting, maybe it's good to go back 5-6 years. Then all the black holes we knew, stellar mass black holes, are shown in this diagram. It's an outreach diagram, so the axes are not fully meaningful. You see here the different black holes that are sort of 5-ish solar masses, and 10, 11. The last two have very uncertain masses. These were the black holes that were known because they are in binary stars as well, my favorite topic. And we know them because they were fed by such a stream of mass transfer, and that would shine in X-rays. And if you measure this very carefully, you measure the motion of these other stars, you can work out the masses of these black holes. So that's not many, barely 20, and the last two are questionable. So in 2015, we had the first detection of gravitational waves, and here it is. So these were the masses of the first detection, two incoming black holes merging together to make a very massive black hole. So there were about 30 solar masses. And I hope you can see the excitement at that time, right? These were black holes that were so different from the ones that we saw in our own galaxy, even including the error bars, they were not getting close. And so I think this is huge excitement, and also made a big change in my career. Sometimes you have to be lucky, but I was working on binaries, and it really turns the topic of binaries also to the center of attention. People got excited from all sides. Also, this cannot be, this is so different when people say this has to be primordial black holes. I don't believe that is necessary. I think we can make these from stars we just had never seen beyond our own galaxy. And the galaxy is a lot more interesting than just what we have in our backyards. There's black holes all throughout the universe that formed through different conditions, and from more metal poor gas, for example. And just to show you where we are today, this is where we were 6 years ago. And this is all the neutron stars and black holes that were known at the time. And so the same as I showed you before, but slightly different. Again, the left axis is how massive they are in solar masses, and the position on the x-axis is not meaning anything, just to show you the distribution. It's a very nice outreach image from the Northwestern group here. So this were the first 3 detections. On the left, this was the first event, which was most off. And the second and the third event, you see they're more closer to the ones we know, showing it's probably not a completely new population. We're just lucky to get such a strange one first. But it turned out not to be that strange. This is after the second observing run. And this is where we are today. And, well, I don't know. This is just fascinating. We suddenly populate this full of stellar mass black holes. And of course, my group in Munich and many groups around the world are terribly excited to understand how these form and what we can learn about massive stars and how they work. And it is my last slide on my science, and then we switch gears a little bit. This is not it, right? We're halfway the third run, and we'll soon get the second half of the third run, and then there will be upgrades of the detectors. And so this diagram gives you a bit of a feeling what will happen in the future. So where we are is the third run, so that's 03, that is this light blue line. So we're looking out to redshift of almost 1 for these black holes. So the detectors that are in the making include the design sensitivity, and then on longer timescales, people are discussing 3rd generation detectors. And so what this means is that we can reach out and see mergers of black holes all that way to redshift 10 or beyond. And for most people probably know that there was not much stars before redshift 10, right? So we can probe the whole universe that is relevant for star formation, basically. Going back in time, we really go back to the early days of the universe. I want to switch gears a little bit, and let me first, this event is about Heather and Lauren, who are winning this prize. And I think what I share with Richard Thomas and Cecilia Payne, but also with them, is an interest in what stellar things do. And they may sell their research differently, but I enjoyed getting a little bit of a feeling for what you did. I haven't fully read your papers, but I know that Heather has been working on stars in the very extreme conditions in the centers of galaxies. And so that these stars are orbiting a very massive black hole, much more massive than the black hole that I talked about today. And so some of the calculations he did is that these stars can be sent on trajectories heading for this central black hole. Now, that's not a very nice way for a star to die. It would be ripped apart. We call it tidal disruptions of stars. It's a fascinating topic, and it's very close to what I like, although she took this from a dynamics perspective. And so Lauren's work I'm also less familiar with, but I know he has been studying how convection works in stars. And so how do these outer layers truly work? And they're much more complicated if you look up close. But I wanted to say that the problems you have been working on are really relevant in terms of also the new data that we're getting and trying to understand how do the physics of stars work under extreme conditions. And, so these students did well. So congratulations to them, and also congratulations to their advisors. Something must have gone well. I want to switch gears a little bit because we're not only here to celebrate the students with whom it goes well, we also have responsibility for all our students, and situations can be challenging. And so this is also, I think, the second passion that Richard Thomas had, to be supportive when challenging occasions arrive. And I showed the picture of Cecilia Payne again, and that was pretty challenging circumstances under which she had to do her PhD. She had to move abroad by herself. I don't know how old she was, but probably early 20s. That is not the time where you Zoom or Skype back home. This is taking a ship and you leave basically forever. So she must have left everyone behind. So these are challenging times, right? I know many of you are probably far from home and maybe even taking a PhD in a different country than where your family is. And particularly in time of Corona, it's very hard to be this far from your friends. Hopefully you make new friends in the place where you are. I wasn't a PhD student anymore, but I just moved to Harvard just before the lockdown, but my friends were in the Netherlands. So this one comes quite close. So there is this quote, which is not a very positive quote, but this is from Cecilia Payne. And so she says, there followed months, she's talking about her PhD thesis, and there followed months, almost a year, as I remembered, of utter bewilderment. And sorry, I'm not laughing for what she says, but the word is not, I'm not so familiar with the word. I'm not a native speaker, as you are aware. And then she says, often I was in a state of exhaustion and despair, working all day and late into the night. And I bet we all recognize this. And at least probably part of our time, we went through moments where we worked as hard as she's writing here. But it raises the question, does it have to be? Right? Is this the way to do your PhD? She did it under extreme circumstances. She was a minority and one of the very few women trying to be taken serious. She had a world's groundbreaking discovery in her hands, and yet some of the biggest names in the field not believing her and probably putting pressure on her to say that it is probably an error in the theory, or maybe even making her believe there's an error on her side. And now we know, if you know her story, is that she actually discovered what the universe is made of and just changed completely our worldview, right? So she clearly did her PhD under very challenging circumstances. I hope that's not the average circumstance we go through. And so for the second part of my talk, let me say again, I'm absolutely not an expert on this. I learn every day more about supervising students, I learn from my mistakes. I learn from the successes as well. I think it's important to focus on those as well. Preparing for this, I found the articles again. I had seen them before, but I want to quote them for you so you're aware. This is a survey done by the Nature Journal, 2019. So it's a survey among 6,000 graduate students. And the good news is, the majority is very happy with their experience of research, which is great. But then 1/3 sought help for anxiety or depression related to their PhD. That's a big fraction, I think. And so it's not one study, right? So this is a different study, much larger, 50,000 graduate students in the United Kingdom. Again, 80% is positive about their research experiences, yet a whopping 86% reports levels of anxiety. And just in case you're wondering, these are young people, adolescents go through anxiety probably also when they're not in PhDs, but this percentage is a lot higher than what is normal under the normal population. And so here's the third study, basically saying the same. This is a Belgian study. And so they find 3 things. 1 in 2 PhD students experience psychological distress, and 1 in 3 is at the risk of a common psychiatric disorder. That's insane numbers, right? So they compare this with, so here they specifically compare with highly educated general population and highly educated employees and higher education students, but it's severe for PhD students. And so they also try to investigate what does it correlate to. And PhD student advisor interaction is clearly one of the aspects that plays a role there. Just to summarize, most of our students are happy with research, yes, the studying fraction experience psychological distress. And I don't know how many of the seniors are online and think back of their own PhD, and we all went through stressful moments, obviously. I don't think the situation is the same for when we did our PhD and how it is to do PhD today. I'm not saying that I know the circumstances here, but I think it's important to realize that situations have changed and that we have a new generation of students that have new challenges. If we had social media at the time as much as, anyway, many aspects changed. And just to somewhat brighten this up, I think this series of comics has been one of the things that kept me alive during my own PhD, because I realized I was not alone. And so for those who may not know, this is PhD comics. You can find them online. It's a brilliant series, and it's in a light way pointing out many of the things that we go through. But yet, well, it has a funny ending. Coffee solves everything, apparently, in this. But can we only do good research with blood, sweat, and tears? I'm not convinced of that. I think it actually distracts us. But yet, this is the common experience for many of us. And so, I don't know how we want to do this. I know there's people online. It would be great to have some input, and I would like to invite you. I think there's a delay between the streamcast here. I had hoped to have some of you on Zoom so we could actually discuss this. But let me pose this question. I want to invite you to respond to any of this in the chat, so we can have a little bit of input on this side. I think that's what the organizers proposed to me. I don't know how to do a Zoom discussion one way, but I really encourage you. So how shall we do this, Anne? Shall I briefly read this out, or?
Yeah, if you could read this out. Do you have more slides you'd like to get to the end before I kind of ask you some questions, or?
I think this is the point to start a discussion if we manage with the technology that we have on hands today. I have 1 or 2 slides to wrap up, and also some resources, especially if it triggers something.
Okay. Okay, wonderful.
So I think you will watch.
Yeah. So I'm gonna watch the chat, but of course there is a delay. So I'm gonna. I mean, the first question is one I'm really interested in, but I want to start off with asking you about the international aspect of being an academic these days, right? So you did your PhD in the Netherlands. and you moved to the US. You're now in Germany. I think this is, it's not that I think, this is definitely an experience that all postdocs in particular have to go through, being a PhD in one location, sometimes not their home country, and you really have to move now. And that can be exciting, but that can also be really disrupting. So I have a couple of questions. Like, I guess the first one would be, just to start off lighthearted, but are there any interesting cultural differences that you've found in like a mentor-mentee relationship in different countries? I'll ask you a follow-on question after that one.
Yeah, thanks. Again, I'm not pretending to be an expert, so I'll just speak from my own experience. I think the differences between supervisors themselves is probably bigger than the cultural differences or I don't know, gender differences or field differences. We are all people and we have very different styles and different levels at which we, I don't know, are able to read other people's emotions and interact with each other. That said, there are definitely very different cultural aspects. So I grew up in a country that is not so different from the US in style. I mean, it must be a much bigger switch if you come from a non-Western country. The system in Europe is different. People are hired in a PhD and they're almost always specifically hired to work with someone. So immediately when you sign up, you basically apply to work on a very particular project with a particular supervisor. This can be positive and negative. And so the difference in the US, you would be hired into a PhD program and later you will find your PhD supervisor, right? This has positive and negative parts, right? It can be in Europe because you're really going for a particular advisor, that this advisor is much more committed to help you and help you throughout the PhD. Yet this decision is based on a short interview, and are you really a good match is not always clear. So I think this commitment, I feel, can be very good. What is not good if the relation is not very good, and it's better for you to work with a different advisor that is much more problematic in Europe. And so in the US, of course, it's more easy probably to move to a different advisor in the same department. But if there's not a good match for you in the department, you're still in that particular program. It can be hard to find someone that fits both your scientific interests and the mentoring needs that you look for.
So we do have a comment. Thank you, by the way. And I didn't thank you for your talk. I'll thank you for your talk later. But we do have a comment from Henny Lammers. So he says, it's important that the advisor makes his PhD and graduate students into a group of friends with regular social activities together. Would you agree with this?
It's a lovely statement, and it's nice to hear this comes from Henny Lammers. He was one of the professors in Utrecht that I had high respect for. I wasn't part of his group, but so that's an interesting statement, right? I agree, but I don't know if all advisors agree. I think advisors may have different feelings about how far their role goes towards socializing and asking about the psychological needs of their students. I think this is definitely part of our role, but we're not trained to take on these roles, right? At least I'm trying to educate myself, but I was probably mostly selected for my science, and
I totally agree. I meant to like be an MC and not just like, here's what I think, but here's what I think. Just in the same way as I was never like trained how to code, and yet that's what I did for all of my PhD and postdoc. I feel like, yeah, we're a really important role now that we're at faculty level is mentoring, and there's no training. Like we're just people who are in the role.
It's not an excuse, right? So maybe we feel we're not trained for this, but yet our professional role is that we mentor students, and whether we're good or bad at that, this is our professional role and our duty and our obligation.
No, that's a really good point. I completely agree. But just as I figured out how to code, you have to figure out how to be a good mentor as much as you can.
I think this triggers another thought I have. So these numbers are so crazy high. The number of students that is like 2/3, more than 2/3 has some distress, right? And I don't think we can always blame the advisor, but the relationship between advisor and PhD student is an intense one, and so it will always play some sort of role. So I think the important thing, maybe it's a lesson for myself more than anything, is however much you care and you think you try to do the right thing, these numbers are insanely high, and so they also affect the groups where the relationships are good and where people actually care about their students. Mm-hmm. Right? This is 2/3 of the students. That's the students that actually enjoy your PhD are the same students in part that go through depression, and I don't know how well I have appreciated that so far, and maybe that's true for other colleagues around me as well.
So I'm interested in asking you about all of these questions. I know, okay, the first one is actually really tricky to answer, so feel free to pass, but do you think a PhD going through grad school is inherently challenging, I think is accepted, but inherently bad for your mental health? Like, what is your opinion on this?
Yeah, I wish we had more interaction from a larger audience. I think I definitely should not be speaking on this. I had an advisor that definitely cared a lot about me, and I'm immensely grateful for what I learned, but it was still a stressful experience to go through, right? You're young, there's all this pressure and expectations. You don't quite know what your advisor wants from you or what is expected to succeed. I definitely think it doesn't have to be. There's no reason that good science comes from suffering or something. That's something I absolutely not believe in. Completely avoiding it may be hard, and I bet many advisors are really trying to do the best for the students and care and try to look out and, as Henny Lambert suggested, try to make friends with them. But I bet that even in these groups, there must be a large fraction that goes through this very stressful periods of time. So,
and what about the role of the department? Do you have thoughts on what a department as a whole could do?
I don't want to do that. Andreas, would you like to speak to this, or can we involve you in the discussion?
Okay, the role of the department can play a role in this actually, because it can help actually that the graduate students are not only maybe mentored by one research advisor, but that they are helping that the graduate students can form a group, that they are recognized as a group in this, and that they can have also spaces within the department where they can talk to each other, where older graduate students can help younger graduate students, incoming graduate students, and also so that you have the space and the freedom actually that they can talk among themselves actually, and that you are not feeling alone. So I think the department can play a big role in this one, in this direction actually. And certainly department has also to play a role in this, that they're looking out if something is happening, and if there's a graduate student that is recognized that the relationship between a research advisor and a graduate student does not work very well, there are certain means that one can try to interact actually. Besides this, I feel as research advisors, we have to play a role in this to accept that our graduate students are not only, they're researchers and they love their research, but that's not all. They have also life outside of research, and we have to acknowledge this. And whether we are, we try to socialize a lot with them, but we have to accept that they have a social life actually, and social life sometimes plays a big role in their development. That's just some of my thoughts, but I'm also not an expert in this. I'm like the two of you. I'm learning.
Yeah, fair.
We do have a couple of comments, if I could just jump in. So a perhaps significantly underappreciated or not well-known fact about Richard Thomas is that he was an unwavering supporter and admirer of women in science. He judged people on merit, aptitude, and character, and did not tolerate discrimination in any form. Another comment that we have is, thank you for bringing this up, Dr. de Mink. I think that's, yeah. I think this is not a conversation that we often have as scientists, and it's really important.
Things I've seen people in department. So I've moved department a few times, and in some places there was a lot of attention for this. In some places slightly less, but people were learning, and everywhere it's with the best intentions. I think even in the moments when a particular relation between the PhD and a student and an advisor clash, in almost all cases, I think there's still the best intentions, but they don't always work out as well. What I found very admiring in one of the departments where I've been, some of the faculty were very open to discuss that the PhD and their own career was not without mental health challenges. And that's quite a personal thing to talk about. I was a young assistant professor at the time, and I didn't necessarily want to share how hard it was for me at the time, but I was very glad my more senior colleagues were actually sharing this with the students. And so that doesn't solve the problem, but it helps if you understand that mental health problems are not taboo. And I'm not just talking about, there's different levels, right? There is not feeling well for going to work or being bad mood or not sleeping well. And there's levels at which you are at a severe depression and really in need of professional help, right? But I think the whole stretch is something that we don't need there. Andreas, I wanted to respond to you because I think the next slide I have another cartoon from the PhD comics, which is almost literally what you were just expressing. So I thought that maybe it's a nice bridge. So the left is the PhD student seeing herself with a very complex human being full of hopes, dreams, and aspiration. And then the professor, how do they see you? Well, it's just a brain on a stick, and how's your research going? And
it's a wonderful comic. And, yeah, and exactly like this, we should not see our graduate students. It's not just about picking their brain. Yeah. They are whole persons.
So we only have 3 minutes left, unfortunately, so we're going to have to move on. Thank you everybody for your comments, and this is an ongoing conversation at GILA and in our departments. Yeah,
let me say this. I know, I don't know who's watching and what's the range of people there, but given the statistics, there's a good chance that 2/3 of you is suffering at a different level, and that maybe 1 out of 3 of you, if you're a PhD student, actually needs help. If you're at Boulder, these are the resources where you at least can find counseling. I know this can be a very big step to get there, but if things are seriously unwell or you're really worried about a friend, try to help them to find these resources. And I don't know if there's people in the department that can reach out to Anne-Marie, but I know statistically there will be a few people there that really need help at this moment. So, yeah. Oh, and I want to advertise one thing that I have nothing to do with, but I just admire this so much. You might have seen this, but there's a group of students that actually took action. I think it's what can students do? Actually, students are not only able to change their own department, but I think they can make a difference on an international level. And so this is a group of students and early career research that took the initiative to ask for time at the EAS, the European Astronomical Society, to have a session specifically on topics of well-being and astronomy. I know many of the organizers, but I have nothing to do with this, but I'll certainly be listening in. I think this will be of great help to both PhD students or advisors that want to understand more from this. So that was it from my side, and I'll leave this up so you can find the link.
Yeah, that's wonderful. And thank you. That's on Monday next week. So that's oh no, in June. So that's fantastic. Okay, so unfortunately we have to wrap up. So this concludes our event today. I want to, of course, thank our guest speaker, Dr. Selma de Mink, Andreas Becker, Professor Andreas Becker, as well as our past and current recipients of this award. And thank you also to JR for technical support. this YouTube live event streaming from a Zoom meeting. It will be wonderful someday to actually be back in person, but hopefully this went smoothly. I also want to thank Chris Natinsky for putting together this event. Yes, nice slide to and finally, thank you so much to Dr. Nora Thomas, who funded today's event. We were delighted to announce that Dr. Thomas will be making a generous gift to this award to increase its endowment. And if you would like to learn more about how to get involved at JILA, we wanted to say, please reach out to Chris Natinsky. His information will be in the chat window on YouTube Live. And yeah, again, thank you so much to our guest speaker. That was absolutely wonderful. And thank you everybody for joining us today.